Welcome everybody. This is the third session of our course. So let me recall you. This is a course on topics on mirror symmetry and Landau-Ginzburg models, and is given by John Alexander Cruz Morales at the University of National University of Colombia. Sorry.
Okay, so thanks, Marina. So thanks everybody for coming. So today I will, discuss some relationship between the Landau-Ginzburg models, particularly the Laurent problem we have been uh, studying, and the so-called exponential periods, right? That I guess that there is this connection will be like, in the setting of studying arithmetic properties or arithmetic phenomena behind mirror symmetry. So let me just start uh, telling you the definition of a period according to Concevich and Saget. So Concevich and Saget, they wrote a paper called actually periods around 2000, and they defined actually this new type of numbers, the complex numbers, which are essentially defined by some integrals. So let me write the definition of period according to them. So a period is a complex number whose real and imaginary parts are values of absolutely convergent integrals. Absolutely convergent integrals of rational functions with rational coefficients over some certain domains, over domains in Rn, given by polynomial inequalities, given by polynomial inequalities with rational coefficients. Okay, so let's do some examples of these kind of numbers. I mean, for example, the square root of 2, you can see that this is this integral 2x squared 1 dx. This is a period. Also, the number pi, you can see the number pi of this double integral over this domain. X squared plus y squared minus less than or equal than 1 dx. 1. There's also other numbers like, log, which is the integral 1 to 2 to dx x, right? And there is this other example which actually will play an important role in the talk today. For example, zeta 3. So the value, the zeta is the Riemann zeta function in 3. So you can see this is this integral minus y less than c less than 1. So dx y z 1 minus x. Let's see. So All of these are periods. These numbers are periods. Periods, right? That's very nice. I mean, because they're quite, cool numbers like, square root of 2, pi, these values of the logarithm, there's values of the zeta function. So in general, you take, for example, the zeta, the so-called multiple zeta values, they are actually periods, right? But so let me make some remark. I mean, you see here, I mean, I just integrate the function I am integrated is just the constant one. This is something we can somehow do always. So let me just write this remark here. So one can write an different period as the volume of a domain defined by polynomial inequalities, qualities with rational coefficients. Right? So we never need to integrate any function more complicated than the one. The constant function one. However, I mean, because that's somehow what I did in these examples. But however, actually today I will see that sometimes, the function we are integrated is really interesting and so important. So I will do an example later where actually it's really, I mean, the function will play an important role. The other thing is like, okay, there's the other remark is that the periods actually, they form a ring. Actually, the sum of two periods is a period, and the product of two periods is again a period. So we have the ring of periods, and so we can denote this by P. This is the periods, the ring of periods, and they are actually countable. So this is a countable set. So P is a countable set. That's important because this means that many important numbers like pi, multiple zeta values, etc. There are periods, but there are more numbers, complex numbers, which are not periods, right? And I will back to that question later today, right? But very important constants and very important numbers in mathematics, they are periods. That's the interesting thing. And we see that there are other numbers that we don't know if they are periods or not, and then we probably need to think about some extension of this ring. But I will talk about this theme later today. So we can probably have more fancier definitions, right? So let me also write this kind of thing. So periods can be defined in a fancier way. Okay. So let me just do it because that will be probably more related with this fancier definition probably will be more related with the discussion we have been doing during these lectures, right? So let X be a quasi-projective, be smooth quasi-projective variety, and take y as a subvariety of x, subvariety, and finally take omega a closed algebraic M form, closed algebraic M form on x vanishing on y. Okay. All of this you can define it over Q bar, all defined over Q bar. So the algebraic closure of the of the rational numbers, and let C be a singular n chain in the complex points of x with boundary contained in the complex points of y. So then you define this integral, the integral where C of omega is a period. But somehow, I mean, this definition actually coincides with the definition of previous, I mean, for the previous definition. So, but that's kind of fancy way to define a period. What is important for us, I mean, one of the important thing for us and for today's lecture and for this discussion is like, that the periods somehow they are solutions of some, they appear as special values of solutions of differential equations. That's the important thing. So periods appear as special values of solutions of certain differential equations at algebraic arguments. What is interesting is that these equations actually, these differential equations, are called or are Picard-Furs equations. So if you remember that we already actually made Picard-Furs equation before, when we were defining the classical period, and there should be some. Now you think so. We define the classical period of Laurent polynomial, and you probably are thinking, okay, there should be some relation between this classical period and this regularized quantum period we defined for the Fanos, in the second lecture, and these numbers were defined here, right? Because again, you remember that we actually saw that this classical period for the Laurent polynomial and the regularized quantum period for the Fano satisfies some differential equation, and the differential equation actually was a Picard-Fuchs equation, right? So we take some this discussion that actually is quite related with the discussion we are trying to do today, because this is exactly the content of what I'm saying here. So you take special values for solutions of this kind of differential equations like Picard-Fuchs. So then we get the periods. Of course, we can get Picard-Fuchs equation beyond a Fano situation because this mirror symmetry for the Fano situation, right? But what's one's source of examples for the Picard-Fuchs equation? So what sort of when place where we can actually find these Picard equations is actually a mirror symmetry for the final manifolds. I mean, this final Landau-Ginzburg mirror symmetry. Of course, I mean, we studied the Calabi-Yau mirror symmetry. We also have the Picard-Fuchs equation, and we also have periods there. Again, you remember the first lecture when I described mirror symmetry for Calabi-Yau. I said, okay, mirror symmetry can be understood as kind of relationship between the periods in the V model and the Gromov-Witten in the A model. So again, this idea of periods appear there. And the differential equation satisfies, in this context, is again a Picard-Fuchs equation associated to the mirror family in the Hodge theory side, in the B model side. So that's actually somehow the idea behind, yeah, right. So I want to study. So we already found this kind of differential equations for um, in the context of the final. So I use one to describe one particular example, which is actually interesting from the point of view of the, I think, number theory, and and it's very interesting mathematically. And actually, at least from my point of view, it's a good example of the power of mirror symmetry and how actually the geometry behind mirror symmetry actually interact with deep arithmetic properties and deep arithmetic questions about periods and about also uh, varieties, etc. Right? So let me say that one interesting example. So one interesting example of the Picard-Fuchs equation. So at the end, we will see that we are not far in from the Fano Landau-Ginzburg model mirror symmetry. So at the end, we will see that actually this example is in the Fano and Landau-Ginzburg model mirror symmetry. Okay, so an interesting example of Picard-Fuchs equations and you know Picard-Fuchs equations so and their relations to periods is um, is given by the Aperi differential equations. So let me just say a little bit using what about this Aperi differential equation. So you know that so it was known from the I think from Euler probably, right? That the zeta 2 is irrational, right? It was known, I think was known maybe before Euler, but certainly Euler know that this is irrational. Right? This is known because zeta of 2 is equal to p squared over 6. And then we know the pi is irrational, so this number is irrational, right? Good. In fact, I mean, you take an even number, so you take the zeta value of an even number, right? So n is a positive integer. This is irrational, right? Because it's known that actually this number is pi squared times some rational number, something like that, right? So we know that these numbers are irrational. Good. But the next question is how about zeta 3? So zeta 3 is irrational. But actually, the proof of this is not that old. It's a little bit old, but if you compare with, the rationality of zeta 2 is not that old, because this is actually given by Aperi 19 78, 90. Probably the proof was presented in 88, but was published in 89. Doesn't matter. So Aperi actually proved irrationality, and that's what I want to discuss, how the idea behind his proof, and the proof was really mysterious, and it still is mysterious, right? I mean, and I read that someone actually asked to Apari, how do you get this proof? And his answer was, okay, I got it from my garden. It was actually some kind of magic, the proof. This is very interesting, and because of that, I mean, there was a lot of interest in his proof, and that's what I want to discuss in a second, right? It's very, very remarkable proof. For other values like zeta phi, 7, etc. So the question is open. So we don't know if they are irrational or not. There's a lot of, people have tried to use the Aperis idea to prove the irrationality of zeta phi, zeta 7, etc. But they actually fail. So far, actually, it seems we cannot extend the Aperi proof to other values. And my impression about that, my guess about that, is because the geometry behind the proof of zeta 3, which I try to, I will try to discuss with you today, is too special that maybe it's not possible to extend to other values. Of course, I mean, you can have a proof of irrationality, similar proof of irrationality for zeta 2, and actually Aperi did, right? And zeta 2 and zeta 3 seems to be very, very particular. And my guess is that the geometry is too special. So the mirror symmetry actually, in fact, should actually explain why it's too special. And then we cannot extend to other values. But maybe, so, the Landau-Ginzburg models we will discuss next week probably will give the geometry we need for other zeta values. I don't know. I mean, it's just an speculation, but let's wait to the next week to see what happened with other kind of Landau-Ginzburg models, right? Good. So let me just try to see this irrationality. This is really interesting. Okay. So what Aperi did was the following. So Aperi proposed the following recursion. So Aperi, and this is the magic because he didn't actually explain how actually he got this recursion formula. And it's very special recursion formula. So Apari proposed the following recursion formula. Okay. M plus 1 cube u m plus 1 minus 34 n cube plus 51 n square plus 70 27 n plus 5 un plus n cube un minus 1 equal to 0 and bigger or equal than 1. I mean, I will call this formula asterisk. Okay? One interesting thing, what is important in the proof, is that every solution of this recursion, so every solution of this recursion satisfies un, close to some constant n minus 3 over 2 c plus n minus n. And this here, this c is this number 17 plus 12 square root of 2. I feel like I don't want to discuss, in detail the proof. But actually, this particular value of C is very important in order to measure the rationality of C of 3. So this is not really this is not an arbitrary number. It's the precise number we need actually to get the 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 measure of the rationality. So we actually this is very particular. I mean, this is very very particular. It's very particular recursion. I mean, so that's one of the mystery. One of the mystery. Okay, so we can actually define an aperitif. So aperi actually define two solutions. So one can define, but actually aperi did can define two solutions of the recursion formula and their generating functions. The generating functions. What actually the recursion? So number here to 0, infinity. So okay, sorry. A01 is 1, A1 is 5, and the corresponding generating function is AT is and n equal to 0 to infinity, that's 1. And the other is the Bn n equal to 0, infinity, B0, 0, B1, 6. And of course, we have Pt. But in fact, Aperi did much better and gave precise, closed formulas for An and Bn in terms of some binomial coefficients. So we can do it much better. So in fact, Aperi gave the numbers An and Bn, the explicit formulas formula in terms of binomial coefficients. So this is not really important for our discussion, but I will give you the expressions just to see how actually these An and Bn are not that, I mean, in certain sense, trivial. So An is not that complicated. So An is just this sum, L equal to 0 to n L square, n plus L square, n bigger or equal than 0. So that An is not that complicated. Bn is more complicated. So let's write Bn. This is more complicated. Again, it's a sum, L equal to 0, n is Ln square, n plus L square. But there is a new factor here, I will write here. So there will be sum n equal to n 1 minus L minus 1m 1 over 2m squared nm n plus m. And again, n is bigger or equal than 1. So Aperi got this thing. Actually, I didn't say that, but the Aperi's proof is just 2 pages. It's really short. He didn't explain anything. He just gave the formulas, showed that the formulas work, and get the rationality of zeta of 3. No explanations in Aperi. That's the important thing, right? One of the key points in the proof is the following remark. So this is an important. Sorry, okay. Oh, so my tablet is oh, sorry.
Suddenly you're not sharing.
John Oak is not sharing. Sorry. Okay, something happened here. So. Okay.
Here, you're back again. Yeah.
Thank you. Sorry. Today was the technical problems day. So, okay, good. So you have that. The important thing is given by this remark. So this remark, okay, I don't know what happened. Something is not working with it. Okay, now it's again. So the important thing is this remark. This remark is important in the proof. You take an theta 3 minus bn, but actually this is something that you want to see that some limit is going to zero. That's important for, that's actually the fact you want to construct the proof. But what is important for us is that this number is again a period. This is a period for any n. This is important. And that's interesting because it is a period. So what does it mean? We can write this as an integral. So let's do that. So we can write this number as an integral. So we have that again, theta 3 bn is equal to the following integral. 1/2 0 1 0 1 0 1 x, sorry, x y z 1 minus x y 1 minus y 1 minus c over 1 minus c plus x y z, and here we have to put the 4, right? Is this integral, right? So in 1984, Boykers and Peters, or 1984, so they want to actually to understand a Paris proof. So they want to see, okay, what is the reason of this proof of this recursion, or why this proof actually works, and they want to extract some geometry, study the geometry behind this recursion and these solutions and this Aperi's idea. So in particular, so they study this integral, so they propose to study this integral here, but they want to study using kind of one parameter, actually one parameter family one of this integral. So they introduce a parameter t and study this integral with respect to this parameter. So these workers actually and this Peter, so they study this integral expression with Tn is a parameter for any n bigger or equal to 0. So they get the following thing. So they get that we put everything in terms of this So we can write this integral the following way, somehow the same thing. Same thing. Yeah. But here now you have a sum. Okay. And we have this x, y, z, 1 minus x, 1 minus y, z, again, 1 minus x, the same. But now we have here, let me put it with other color, maybe with blue. Now, okay, it's not showing you the color. Blue is Tn. So now we have this Tn. And again, we have the following. We got the other things like before. So they get this integral. But they actually saw that we can rewrite this integral in a better way. So they actually got the following expression for the integral. So 1/2 0 1 0 1 0 1 dx and this denominator 1 minus z plus x y z minus t x y z and how to put here this product 1 over 1 minus x 1 and 1 minus. So they want to they wrote this integral and they said, okay, look at the denominator of this integral here. Look at this denominator. So actually this denominator we can use this denominator to construct a family of varieties of C3. That's what they observe. So if you look at this denominator, so we consider the following family. So consider the family of varieties on C3 given by the following things. So the points x, y, z in C3. And we use this denominator to define the family, right? So 1 minus z plus x, y, z minus t x, y, z times 1 minus x, y minus y equal to 0. So we have this family defined by this equation, right? And this is a one parameter family. So with parameter t in P1. So we have this one parameter family. So after projectivization, and resolving some singularities, and resolving all singularities, what we get at the end is this gives a family of K3 surfaces. So we have a family of K3 surfaces out of this uh, Aperture proof somehow, right? So, but what we want to claim, or what I want to claim is like, actually Boykers and Peter did was okay. the geometry behind the rationality proof of Aperi is related with the geometry of this family of K3 surfaces, right? This is kind of the pencil of, it's a pencil of K3 surfaces. Correct? But this is not really an arbitrary pencil of K3 surfaces, right? In fact, this was not an observation by Borges or Peters. This is an observation that came before. I learned this from Golicek and his collaborators. I don't know if it's before then, but it is not really an arbitrary. But of course it was before, but it was not actually an arbitrary pencil of K2 surfaces. This pencil actually, if you look at this as a kind of family, this pencil actually is this pencil is the mirror of a final trifold. In fact, the so-called B12, the so-called B12, final trifold B12. Right? So the Picard-Fuchs equation in by Aperi or the Aperi-Picard equation is the regularized quantum differential equation for this trifold. Quantum orbital. So the rationality proof of theta 3 is closely related to the mirror symmetry of B12. That's really interesting. That is really, I mean, the first time I saw this it was actually very surprising. This is really surprising. Let me just make this remark. We can do it the same for theta 2. So similar arguments works for theta 2, right? But now we don't get a family of K2, so we get a family of elliptic curves. A family of elliptic curves mirror to global of P2 in 4 points, or which is M05 bar. That's very interesting. So the irrationality, the upper proof of irrationality of theta 2 is related to the mirror symmetry of M05 bar, and theta 3 is related to the mirror symmetry of the quantum triple P12. Of course, you can now speculate and say, okay, if I want to prove the rationality of theta 5, there should be now not a Fano threefold, but a probably Fano fourfold, right? And then the mirror of this, there should be some pencil of Calabi-Yau threefolds, and the Picard-Fuchs corresponding to this pencil of the threefold should give us the rationality of theta 5. I mean, in principle, maybe you can write this kind of thing. The point is that so far the integral is not it does not converge fast enough to get the rationality of C to 5. So you can get this integral maybe, and then you see that this actually converges to theta 5. That's probably something you can do, but the convergence is not fast enough. So this thing, it seems this is very particular for theta 2 or for theta 3. For me, it's actually a mystery, and I think it's a bit interesting problem, an open problem. And maybe the right angle will be like not try to extend the upper is proof to other values, but try to explain why is too special the upper is proof that only applies for this particular, mirror for this particular funnels, right? That will be one direction. The other direction is okay, maybe the irrationality of the odd zeta values is related with the geometry with some Landau-Ginzburg models, but maybe we need to go beyond the Landau-Ginzburg models mirror to funnels and try to explore other kind of Landau-Ginzburg models and try to see if the geometry behind that can help to get the rationality. You know, next week I will try to discuss with you another source of Landau-Ginzburg model mirror to other kind of families which are not funnel that I mean potentially could give some ideas in this direction. In any case, this is a really interesting problem, right? So we see so far we have seen that there is this relationship between periods in the sense of conservation again and mirror symmetry for Landau for Fano manifolds or Landau-Ginzburg models, for example, via this Aperis proof. But the title of the talk today was exponential periods, and I haven't said anything about exponential yet, right? So let me go to this question. So I said that the ring of periods is countable. This means that there is a lot of there are really many numbers, complex numbers which are not periods. We can ask, okay, which numbers are not periods. So in particular, we can ask questions. So we look at this very interesting constants, no? Square root of 2, pi, log of 2, zeta values or multiple zeta values. Very interesting constants. But there is this also very important constant in mathematics. It's everywhere, these numbers. So the number E. So we can ask, okay, is E a period in the sense of conservation again? So the answer is we don't know. So far nobody has found some integral representation in terms of for this E in order to make it a period. So we don't know. But the expectation is that the answer is not. So the expectation is the answer is no. We expect that. So we expect that. We expect that E is not a period. It's not a period. That's the expectation. So actually conservish. So but we want to probably to extend the ring of periods in such a way that include number like E, because again E is kind of very nice number in mathematics. Why not? So actually conservish and Serge, but it was probably only conservish, but it's in the paper. So let me just conservish Serge. Propose to extend the ring of periods to the so-called exponential periods. And I will give you the definition of exponential period in a moment. But I think the idea of the exponential can actually came because related with the exponential function. So we need to include somehow this value in. So this extension actually will include E, but not only E, but other, interesting constants coming from values of the gamma function and coming from another sources. So the idea that the most important constants in mathematics, for example, also the Euler constant will be exponential period, right? So what is that exponential period? So I will give you the definition in the in Consevich and Sayé paper, right? So an exponential period, exponential period is an absolutely convergent integral, convergent integral of the product of an algebraic function, okay, with exponent of an algebraic function or a real semi-algebraic set where all the polynomials enter in the definition have algebraic coefficients. That's it. So what does it mean? So exactly what does it mean? So this means that the exponential period is the following numbers. So this means exponential periods are numbers of the form the exponential periods are numbers of the form e minus f omega g. So this g, the domain of integration is or n semi-algebraic in the intersection where the intersection of the algebraic closure of Q with the real, and F is just a function, rational function here with Q coefficients in Q bar levels, and omega is a rational algebraic differential form over Q bar. Okay, okay, such that this integral should converge. The integral converges absolutely. That's the the periods, the exponential periods. So this is really keep in mind this formula here. So that's the exponential period. So in this sense, I mean, with this extension, so the number e will be a period, and another interesting um, mathematical constants, there will be a periods in some kind of adequate sense. We this thing of exponential periods, right? Let me just make some remarks about this definition. So there's an important work about these things. So there is other approaches of these exponential periods. There is a recent paper by Comelin, Haberger, and Huber. So they read a paper called somehow exponential periods and minimality. So let me just make some kind of, window about this. This is very interesting because, this minimality is something that came from model theory, from logic, right? And essentially, this is related with, or it's kind of, how can I say, it's kind of a manifestation of the time geometry envisioned by Grothendieck during the 80s. Probably the skis of a program, which was this Grothendieck's text he wrote in the 80s when actually he wanted to study the geometry of the model space of genus zero, actually genus G and N-mark points curves. If he wanted to study this, and he, relates this with deep questions about the Galois, the absolute Galois group of the rational numbers, and he introduced an abelian geometry and another interesting pieces of mathematics. One of the things he actually tried he actually found studied this, or trying to study this geometry of the smaller spaces, was what he called time geometry. So he wanted to say that there is this, in the usual topology, there is this kind of pathological situations like, the piano chord or things like that. And he wanted to take out this kind of, strange situation from the topology, and he proposed what he called time topology, which should be something more. I mean, the object will be time, and not this kind of wild objects like the piano chord or things like that. Uh, Somehow the one realization of this program is in logic, and it was this idea of minimality. Recently, thanks to works by Pila, Zimmerman, and another people, so this minimality has been very useful to solve problems in Diophantine geometry and in Hodge theory. And this paper by Kamelin, Hebeger, and Huber is try to like this, idea of time geometry, or you want or minimality, in terms of studying these exponential periods. In fact, they define a new version of the exponential periods. So they define, so in this paper, Kamelin, Haber, and Huber define what they call, um, okay, define the so-called generalized naive exponential periods. So kind of integrals. And somehow you can ask if these naive exponential periods, or these generalized exponential periods, are the same exponential periods in Concept sense. So there is a conjecture. So conjecture by Johnson that all periods in the sense of Concept are these kind of new generalized naive exponential periods. There are certain intervals. This is one approach. The other remark is, in fact, Johnson and Fressan, so Fressan and Johnson, they haven't actually studied the exponential periods, but from more algebraic geometry point of view, actually they study exponential periods, study. So they define exponential motifs, and then using these exponential motifs, they study the exponential period. So they want to see that the relationship between the classical or the usual periods and motifs, they try to extend this relationship between uh, periods and motifs to the world of exponential periods, and they define this exponential motif. This is a very interesting work, hard to follow, but I guess that it's very has very potential, applications in things like mirror symmetry. But still, this is to be explored. One of the relevant points is that the geometry here, so the relevant geometry is the geometry with potential. The geometry with potential. And you remember, I think it was in the second lecture, I called this geometry with potential somehow the geometry of the Landau-Ginzburg models, right? Because what in the usual, you know, uh, motifs and you study some kind of comparison between cohomologies of varieties, etc. So now you don't need to consider only varieties, but a variety with a potential. So we essentially a Landau-Ginzburg model. So what we need to study here is a pair BF, where B is an algebraic variety, not an algebraic variety B or some field K. You want the complex number, but not need the complex number, so any field. And a regular function F, regular function F on B. So in fact, you have the geometry, what we have here in the Landau-Ginzburg. So Landau-Ginzburg models are instance of this kind of pairs. So this theory of exponential motifs and exponential periods is really related to the Landau-Ginzburg models, and in particular to the Landau-Ginzburg, to the mirror symmetry, to the Landau-Ginzburg associated to Fano. So let me just mention this kind of thing. Okay, so we present some picture of mirror symmetry. So I gave some picture of mirror symmetry for quantum manifolds, emphasizing the fact that you can regularize the quantum differential equation, and then when you regularize the quantum differential equation, so you get the Picard-Fuchs equation associated to the classical period of the the Laurent polynomial mirror to the fact, right? That's that's what I did. But how about if you don't get this regularization? If you compare, if you don't want to compare the regularized quantum differential equation and you want to take the actual quantum differential equation for the fund, so what you get? So coming from Giventhal, Hori, Bafa, and other people, so you mentioned Giventhal, Hori, Bafa, also Iritani. So Iritani is someone who actually works a lot in this direction. So Hiroshi has many interesting works in this direction. So Iritani, maybe another people, but so we can have the following picture for the mirror symmetry. So the mirror picture between the final manifold X and the Landau-Ginzburg model YW gives the following. You have the quantum D model of X, This is the quantum differential equation, not the regularized one. So this is the quantum, the model is mirrored to the following D model, the D model of oscillatory integrals of this type. E omega W C omega. So this omega is some kind of volume for or some fiber of this Landau-Ginzburg model. So you see this expression here, this oscillatory integrals, and you see this, let me see, this expression here, right? So they look quite similar, right? I mean, it's exponential of some function and take the integration. So roughly speaking, here is the same. So we have the exponential of some function. Somehow this function actually came from the middle of the funnel. So certainly we don't take the regularized versions. We take the the quantum D model for the funnel. So we see that this is the solution of this thing. So other way to see is that the J function, you remember I defined the J function. So this quantum D model is another way to talk about the different quantum differential equation. So the J function was a solution of the quantum differential equation. So you take this J function and you take these oscillatory integrals and oscillatory integrals satisfies the same differential equation. This is what I am saying here, right? Somehow that there should be some close relationship between exponential periods coming from the Landau-Ginzburg mirror to the funnel and the Gromov-Winding invariance or the quantum cohomology of the funnel, right? So if you don't regularize the picture as I did in the second lecture, so if you don't consider taking the classical period for the Landau-Ginzburg model and the regularized differential equation, but instead you consider the oscillatory integral given by this Landau-Ginzburg model and compare these oscillatory integrals with the solutions of the quantum differential equation with the J function. So the relevant, let's say, numbers appearing there are exponential periods. This is what this picture suggests, right? So we should actually interpret and put into the picture so exponential periods instead of periods for the funnel using these things, right? One of the nice, applications, let's say like that, or one of the nice consequences of this picture is given by the following thing. So I will actually finish just mentioning this thing. So let me just make this application to what is called the mirror symmetric the mirror symmetric gamma conjecture. Oh, this is something done by Iritari. What essentially is this thing, actually? Let me just say in words. So when you have hash theory, so you have an integral lattice in the hash theory side. So you can ask, okay, how will be this lattice in the A model side when you look at the quantum cohomology? What you see is like you need to correct the lattice by the so-called gamma class that I will define. I will define the gamma class. So the gamma class gives you some kind of correction for the lattice, and it's actually giving you the integral structure of the quantum cohomology. So why you want to have this integral structure? Because this is something you really need. Actually, a rational structure, but particular integral structure, you need to really define the so-called non-commutative hash structure in the A side. And it has deep information about these differential equations. So, this quantum differential equation and its the regularized version has very particular properties in the monodromy. The monodromy has some integrality behind, and this integrality actually is controlled by this gamma class, right? And how this gamma class behind, or what is the origin of this, gamma class, and why this gamma class is in charge of the integral structure is somehow the content of this gamma conjecture, which this is related with the Dubrovin conjecture I mentioned in the second lecture. So in the second lecture, I mentioned that there should be this kind of conjecture coming from the homological mirror symmetry, which relates non-commutative hash structures at triangulated categories. So essentially, one part of this Dubrovin conjecture is equivalent to the gamma conjecture. This is a very interesting topic. I am very interested in this thing, but certainly it is a topic for another series of lectures. I just wanted to mention that there is this relationship between these different things. So let me write what is the gamma con conjecture. So you can define the gamma class. So for a Fano, so if X is a Fano, actually this is also can be done for Calabi-Yau, but let me just focus for Fano. So the gamma class is the following characteristic class. Is the characteristic class this class defined by gamma is this is the usual gamma function, and you have to compute in these Chern roots. I will say what is this. Yeah, have this explicit expression of the exponential of this is the Euler number, the Euler constant plus C1 plus this sum here, k equal to infinity minus 1k, the values of the zeta function at k, right, minus 1 factorial, y the Chern character for tx, the tangent bundle of x, right? And this, okay, C1 is just the Fertian class or tangent bundle, right? These d delta 1 to delta n are the Chern roots. Of the tangent bundle, and this gamma is the Euler constant, which, by the way, should be an exponential period with the definition I gave, right? This gamma is this limit in this number, right? But by the way, this should be an exponential period, right? So this is the gamma class, should be the is related with the integral structure of the quantum cohomology as I said. So what is the mirror symmetric gamma conjecture? Say that, okay. So the mirror symmetric gamma conjecture, gamma conjecture says the following: say that the gamma class of a Fano manifold X, well, X determines the asymptotics of exponential periods of the mirror y w inverse, you have the oscillator integral here. You have this integral here. One dx so synthetics behave like the integral over x z and gamma class of x as c going to infinity. That's the thing. So the gamma class actually is related with this the exponential period. So the Calabi-Yau, the sorry the controls on how how this actually this exponential how the synthesis of the exponential periods actually behave is controlled by this gamma class. So there should be a very nice relationship between this gamma class, gamma conjectures, and exponential periods. And I think that this starts to be explored. So I will just finish saying that there is a Calabi-Yau version of these things, or the Fano, or the gamma conjecture. There is a Calabi-Yau version. Conjecture or mirror symmetry gamma conjecture. I call it mirror symmetry gamma conjecture because there is a way to formulate the gamma conjecture without mirror symmetry. So actually, the original formulation of the gamma conjecture was by Galkin, Golichev, and Iritani, and they only use the quantum cohomology of the quantum manifold. You don't need mirror symmetry at all. But again, I mean, Iritani in his later works show how to give some mirror symmetric interpretation for the gamma conjecture. This is what I wrote here. But you can formulate the gamma conjectures without any mirror symmetry. But there is also a gamma conjecture for Calabi-Yau and the mirror symmetric gamma conjecture for Calabi-Yau. And which is interesting is like Iritani showed that you can derive so somehow the gamma conjecture for Calabi-Yau can be derived from the gamma conjecture of the Fano, right? And the reason is, as we actually discussed, somehow via this regularization, somehow procedure, right? Somehow the key point is that for a Fano manifold, you can consider for a Fano manifold X, you can consider somehow two Calabi-Yau, no? So a Calabi-Yau manifold given either as the total space Kx of the canonical bundle, or as a smooth anticanonical section. So somehow, but it says that this asymptotic behavior, in the case of the Calabi-Yau, you don't need to consider exponential period, but usual periods. And then, but this behavior actually can come from this behavior of the exponential periods given by this thing. When you consider these two, Calabi-Yaus you can get from the Fano, either of the total effect of the canonical bundle or the smooth anticanonical section, right? So there is a lot of questions. There is a lot of work to do, but I think this is really an interesting direction for research to study this for example, to study the approach of using exponential motifs by Fresán and Jossen, and how this actually should has some applications and consequences on this mirror symmetry of the Fano manifolds and vice versa. So you have the mirror symmetry and these Landau-Ginzburg models, how to construct, the corresponding exponential motifs and exponential periods, right? So that's what I want to say today. So thank you.
Thank you. Thank you, Alex. So is there any, let me stop the recording.